Hey, welcome back to Mrs. O'Graham's Maths. This is a worked solution video for the Level 3 Probability Concepts paper from 2018, which is Achievement Standard 91585. One that is about some information on targeting of websites. So just pause the video and have a read if you haven't already. So as a table, so we've got the website is positive or not positive, and it's targeted at general or teens. So we've got 21 of the websites made a positive health claim. So our total for positive is 21. Then we've got, of those, 8 were targeted at teenagers. We've got the 24 is our total for the ones targeted at teenagers. And we've got a total of 70 websites being looked at. We can work out the missing pieces of information. So 8 plus 16 makes 24. 21 plus 49 would make the 70. 46 plus 24 would make the 70. And then we've got 8 from 21 makes 13. 49 take away 16 would be 33. And you can just double check that 13 plus the 33 makes 46 as well. Okay, so then our question is, explain why those events, a website makes positive health claim and a website is targeted at the general population and not mutually exclusive. So we are looking for general and positive. So we have a 13 in there. So the probability of getting a positive website targeted at the general population is 13 out of 70. Since that's not 0, those events are not mutually exclusive. Here, mutually exclusive means they can't happen at the same time. Now, clearly we've got something happening in there with the both of them at the same time, so it's not mutually exclusive. Data from this study support the claim that it is more than twice as likely that a website makes a positive health claim if the website is targeted at teenagers rather than the general population. Okay, so we need to first of all look at what's the probability of a website being positive if we know it's targeted at teens. So we're doing a conditional probability. You can scroll up here to see if it's targeted at teens, the chance of it being positive is 8 out of 24. So we can pop that onto here. Then what's the probability of it being positive if it's targeted at the general population? So general is 46, and those positive ones are 13 out of 46. Then we want to compare those probabilities. So how much more likely is the teen one than the general one? So the teen probability divided by the general probability, and that comes to 1.1795. So is it more than twice as likely? No. It's only 1.18 times as likely, not twice as likely. Again, pause to read the question. I'm going to go straight into the answer for part 1. Calculate the percentage of predictions that were correct, which means that we predicted A when it actually was A, we predicted B when it actually was B, and predicted C when it was C. So these 3 numbers here, the 18, 38, and the 8, are when we were correct. So we do 18 plus 38 plus 8 out of the 100 people that were surveyed. That gives us a chance of 64%. Check on the mark scheme for these as well and show you where the marks went. So we'll just go back and quickly do that now. So in the first part, we had the table of results. Getting that probability correct in the first instance gave us a U, and there was actually an opportunity for merit on that first part too, for a merit point and R point. Then doing these conditional probabilities on the second part got us a U mark. Getting both of them right with a correct conclusion gets us the R. And onto the 64% we just worked out was a simple U mark. To part 2 here, one potential issue with the appropriateness of this model for the different brands based on the data provided here. So first of all, we'll look at the 64% and say that if we're right 64% of the time, then we're wrong 36% of the time. That's a lot of time to get it wrong. Also, the appropriateness of the model for the different brands. So we'll look at how well it predicts for each of the brands. So for brand A, the prediction was correct 51% of the time. For B, it was 88%, and for C, it was 36%. So none of those are particularly good. We could say that it's okay at predicting B, but not at the others. Might support your answer a little bit better. Look at the mark scheme. This one allowed you to get marks all the way to excellence points for this one, where if you calculate at least 2 correct proportions, with supporting reasoning about the potential issues, then you can get yourself an excellence mark. 3 people selected from the survey. What's the probability that the model incorrectly predicted the brand of toothpaste for just one of those 3 people? So I'm going to think about this as being, we could have had the first 2 correct, the last 2 correct, or the first and the last person correct. And what was the chance of doing that? Think about it as being a tree diagram, so getting the first person right, then the second person right, then the third person wrong, and it would look like this. So the first person would be 64 out of 100, then we've removed them. The chance of getting a correct one from these ones is now 63 out of 99 left over, and then the wrong ones left to 36 out of 98. We do a similar thing for the other 2 options. And then we can have either of these branches giving us the result that we were looking for, where only one person got predicted wrong. So add them up since we're doing an OR. So our total now becomes 864 over 1925, which is these 3 answers added up, which if we express as a decimal is 0.4488. And a look at the mark scheme is if we correctly work that through, you can get yourself to an excellence mark. Where we have some information about boys' schools, girls' schools, co-ed, North Island, South Island, and so on. We're going to calculate the probability that the secondary school is on the North Island when it got selected at random. So I'm going to do this as a tree diagram, and we'll first of all set ourselves up with whether they are a boys' school or not a boys' school. And the chance of it being a boys' school is 0.129. Making the chance of it not being 0.871. So then we have either they're on the North Island or the South Island. So we've got the rest of the diagram looks like this. That 71.1% of the boys' schools are on the North Island, so we get this branch and we can work out 1 minus for that one. And then 23% of the other types of schools, so girls or co-ed, i.e. not boys, 23% of them are on the South Island, and take away 1 for this one. All right, we want the probability that the school is on the North Island, so this is this top branch, or this branch here, so boys and North Island, or not boys and North Island. So we get the probability of being on the North Island as being those 2 added together. Oops. So we've got 0.129 times 0.711 for the top branch, and 0.871 plus times 0.77 for the bottom of those 2 branches, and add them together for 0.7624. We'll take a look over at the marking schedule. Here we go, 0.762, and that's a U mark. Okay, now calculate the probability of n given b. So that means given that we know it's a boys' school, what's the probability of it being on the North Island? Compare that to the probability of the North Island to see if they're independent. So those 2 things will be equal if they are independent, because picking a boys' school should not affect whether it's on the North Island if those are independent. So we've got the probability of n from the bit that we just worked out in the first part. And then the probability of n given b is 0.711, because that's the chance of getting an n after we already have a b. So that's this 0.711 there. So that's not equal to 0.7624. So the conditional probability does not equal the probability on its own. Therefore, they are not independent. And doing that correctly gets you a R mark towards your merit. Let's see, and I'm going to do this one as a table. So we've got boys' schools, girls' schools, and co-ed, and then private or state. And we're going to add in the bits of information we've been told. Okay, so got 349 schools altogether. They are either private or state, so that will add up to, like, there's no other types. So there are 16 that are private co-ed. So private and co-ed needs, oops, wrong one, 16 in there. Of the boys' schools, only 1 is private. There are 331 state schools, so that's a total of 331. 71% of the state schools are co-ed, so 71% of 331 is 235. And then what else do we know? So we can actually get this one, this part down here from part A. We were told that the boys' schools, there are 12.9% of all schools are boys' schools. We work out 12.9% of 349, we get 45. Making this 44, and I can go in and fill in the other ones as well, just working through making them add up to their total. Probability that secondary school selected at random is a state girls' school is 52 out of 349. And there's the mark scheme for that question, which can take you all the way through to excellence, because it was a fairly complicated one working out the table. Alright, so part D, have a pause and read it. We're going to explain why the teacher might be suspicious that the student did not randomly select the 50 secondary schools. So this statistics student has randomly selected where we've got 25 schools that were year 9 to 13 in her sample of 50 secondary schools altogether. So what we want to go and do is look at the proportion of the year 9 to 13 schools that we would expect to happen for all the 349 schools that we have. So there are 236 schools altogether that are classified as 9 to 13 out of 349. So the probability of picking a school that is in year 9 to 13 should be about 236 over 349. It makes a proportion of approximately 68% of the total types of secondary schools. If our sampling was fair and random, we would expect that same proportion to come up in the sample, or something close to it. The student has got 50% of their sample, very different to the expected population proportion of 67.6%. So we would expect a sample that has been randomly selected to have a similar proportion to the population, and this one doesn't. The teacher decided to run a simulation to see just how unlikely or likely it is that you would get a 50-50 split. So this simulation is the result of 1,000 trials, and she's randomly selected those schools out of the population to see if we picked those 50 schools, how likely is it that we get a 50-50 split. So this bar, for example, is the number of those samples that contained 30 out of the 50 that were year 9 to 13 schools. And you can see most of the time they're getting to around that proportion of, say, 33 to 36-ish numbers of schools that are the year 9 to 13 group. So based on these simulation results, what conclusion can we make? So the chance of getting a sample with 25 or less of these year 9 to 13 schools is only 0.9%, because only 9 of these samples in the simulation out of the total of 1,000 simulations came out with 25 or less. That's a 0.9% chance. Since this is so unlikely, she can conclude that the student probably did not select their sample randomly. Question 3 gives us some UN estimates from 2018 based on national censuses. And we'll just take a look at the information we're being given. So this is the percentage of the world's population and the percentage of the world's land area put onto the same graph. So South America has 5.7% of the world's population, but 11.9% of the world's land area. And you can make some comparisons there. Then we have the percentage of the population that live in urban areas and those that live in rural areas on each continent. So use the data provided to calculate an estimate of the percentage of the world's population that live in an urban area of Asia. You can see that Asia contains 59.7% of the world's population. So of that group of the population, we then have 49% of them that live in an urban area. So we want to know 49% of 59.7, which gives us 29.25%. The student incorrectly reasons that if you know somebody lives in an urban area, it's likely they live in North or South America. So they've gone and taken a look at this and said, if we know that it's urban, then we've got the highest chances there are 80% and 81%, and so therefore that must be where they live. But this is a question about conditional probability, and it doesn't quite work that way. So what this is saying is that 80% of South America's population lives in the urban area and 81% of North America's population lives in an urban area. But that doesn't tell us anything about the size of North and South America. So they've seen that North and South America have the highest percentage of their population living there, but that doesn't necessarily make the reverse to be true, that the urban population would have a high percentage in North or South America. The conditional probability doesn't work backwards. So we can look and see that the conditions of if they live in South America, they've got a high chance of being in an urban area, but it doesn't work in reverse, that if they live in an urban area, they've got a high chance of being in South America. To do an estimate for the probability that a randomly selected person lives in North or South America, given that they live in an urban area. So actually working out the thing that we should have, that student should have done for the last part. So we've got, think about it as a tree diagram. There could be a North America, South America, or something else. And then of those, the chance of being in an urban area for North America is 0.81, and an urban area for South America is 0.8, just from having read off the graphs and tables at the top. So now we want the probability that they live in North or South America, given that we know they live in an urban area. This is a conditional probability, and this is the formula for doing that. So this is the probability of them being in North or South America and living in an urban area, divided by the probability of living in an urban area. So we get this calculation. So this bit here is from this branch here. So North and urban, adding to the fact that we've got South and urban, so there's the chance there, added up, and then divide it by the probability of being in an urban area, which is the data we were given right at the start of this particular part. That comes to 0.1995. Randomly display some photos from around the world, and we've got a partially constructed tree diagram, and we're going to start by filling in the missing pieces, just making those branches add to 1. Explain how the Google Street photos displayed and the graph that we had from the original stuff of where people live showed that Google Street View does not have photos from all the countries in the world. So we've got, first of all, from graph 1, the total land in Europe and North America comes to 23.2%. If you look back up at the graphs that we had way back up here. So the land from Europe and North America. I'll just go back to here. But if we compare that to, and that was from the 68 plus the 16.4 that I just showed you, we compare that to the Google photos for Europe and North America. So we've got Europe as 0.402 and North America 0.297. Add them together and we've got 69.9% for being in Europe and North America. So this is far greater than their land area of the world. So Google probably hasn't got photos from many other countries. So suppose that we have a photo of scenery. Calculate and estimate that the probability of the location for whether the photo was taken in North America. So it's a conditional probability. We know that it is a photo of scenery, so what's the probability of it being from North America, given that we know it's of scenery? And we've got the conditional probability formula like this. So then we want the probability that it's from North America and of scenery. So North America and scenery, 0.297 times 0.13. And then the probability that it's of scenery, to go on the bottom of our fraction, is going to be all the branches that end in scenery. So Europe and scenery, North America and scenery, elsewhere and scenery, times those branches a long ways, and then add the 3 of them together. So that comes to this bit down here, which gives us an answer of 0.198. A user of the website displays 50 Google Street photos and finds 15 of them were from Europe. Use this information and the other parts of this question to discuss the differences between true probability, a model estimate, and an experimental estimate. Support your answer with relevant proportions. So we've got the true probability can be worked out if we know the information about all the Google Street photos taken. That's if we could collect all of that information, find out how many of them were taken in Europe, and work out an actual probability from them. We don't have the information to do that, so we can't work out the true probability. A model estimate, so on to the next part of the question, can be made if we have a suitable model from a large enough sample, like we had at the beginning of part C. So here's our comparisons with what we did earlier. So we had a large sample here. We were told it was data from a large number of Google Street photos. So we can use that to do a model estimate. So on that model, the estimate for the proportion of photos from Europe was 0.402. Then we can do the website user themselves can make an experimental estimate from their smaller sample of 50. So they just ran one experiment and they get an experimental sample from that. And if we're wanting to discuss and compare those differences, we can then say 0.402 is likely to be closer. So from this model estimate that we had, it's likely to be closer to the true probability because it's calculated from a much larger sample. I forgot to show you the mark scheme for the last set of questions that I was going through. So here is question 2 part D. That expected count for the random sample of 50 schools and the comparison of 67 with 50%. With either a U mark or a merit mark. And then on to the last part there, which was the discussion of the simulation that the teacher used to see just how likely it was that they would get a 50-50 split. And then on question 3, we've got the working out of the percentages for a U mark. We've got a possible excellence on part B, I, and II with those comparisons of the idea of conditional probability. Part C, here's those calculations on the comparison of Europe and North America. Part 2, all of these parts here worth up to merit or excellence. Part 2 again was a conditional probability, so it's really important you learn how to use that formula. It's come up more than once, just on this one paper. And then here, understanding the difference between true probability model estimates and experimental estimates and being able to explain them is worth your excellence. So this video taking you through the probability concepts paper from 2018. Thank you for watching. If you need any more help or revision of any of those parts, go back to my channel and find the relevant video and playlist that's going to help you along with that. Hit the subscribe button down here. Maybe take a look at the suggested videos coming up on the side that might help you out.